Today's session will see the unsymmetrical fault analysis. That on unloaded generator will consider double line to ground fault. Double line to ground fault on an unloaded generator. For that I am showing a system here, that is a generator, unloaded generator, and it is unloaded, therefore IA, IB and IC are once again 0, and the generated voltage and the terminal voltage are same, it is unloaded, therefore A is equal to VA, EB is equal to VB, EC is equal to VC. Then the generator is solidly grounded through ZL. Now I am considering here the fault is occurring between B and C to the ground, that is between B and C and to the ground. And see here there is a fault is occurring between B and C to the ground. Now the total fault current, that is a fault current which is flowing here, is IB plus IC. That is the total fault current here is IB plus IC. That is I am showing here, that is IB plus IC is equal to, that is the IM, that is this is IM. Okay, this is a complete path for the flow of the fault current, and once again it is, there is a complete path. Okay, that is once again you can observe here the fault is involved with the ground, fault is involved with the ground, then the total fault current what you are getting IB plus IC is equal to 3 times IM. That we will see when if I derive the equation for IB plus IC, that is a fault current, that should yields to 3 times IM. Then for this particular fault, then if we are once again if we are defining the boundary condition, here the IA is equal to 0. IA is equal to 0. Then the phase B and C, they are grounded, therefore the terminal voltages are 0. Therefore VB is equal to 0 and VC is equal to 0. And the fault current is IB plus IC. These are the boundary conditions what I am getting from double line to ground fault. That I am listing out here, that is the boundary conditions are VB is equal to VC is equal to 0 and IA is equal to 0. Then I am using the voltage equation, the voltage sequence voltages, that is VA0, VA1, VA2, that is 1 by 3, that is 1, 1, 1, 1 A square, 1 A square A. Here just you have to look into the boundary condition is VB is equal to VC is equal to 0, VB is equal to VC is equal to 0. Therefore here it is a VA, VB and VC, VB and VA, VB and VC, but VB and VC's are 0, therefore I am putting here 0, 0. Once if you are realizing for the, or if you are calculating for VA0, VA1, VA2, what I am getting is the VA0 is equal to VA1 is equal to VA2 is equal to 1 by 3. Just you have to find out VA0. VA0 is equal to 1 into VA, 1 into 0, 1 into 0, that is VA by 3. Then similarly VA1 is 1 by 3 is as it is, and 1 into VA is VA, A into 0 is 0, A square into 0 is 0. Similarly VA2 also we are getting VA by 3. Therefore from the boundary condition VB is equal to VC is equal to 0, the first the relations between the sequence voltages what I am getting here is VA0 is equal to VA1 is equal to VA2. This is one boundary, the relation between the sequence voltages what I am getting. Then we have to look into the current relation. Just I am writing here the sequence, the currents, that is I, IB, IC and its symmetrical components. First I will write for I in terms of sequence currents, that is IA0, IA1 and IA2. Then similarly IB is IA0 A square IA1 A times IA2 and IC is equal to IA naught A times IA1 plus A square times IA2. These are the unbalanced currents, that is IA, IB, IC at the time of the fault. Then I am using the boundary condition. The boundary condition is IA is equal to 0. IA is equal to 0. And also I am putting the value of IA, that is IA is IA0 plus IA1 plus IA2. However, IA is equal to 0. IA is equal to 0. Therefore, 0 is equal to IA0 plus IA1 plus IA2. I am expressing the IA0 in terms of IA1 and IA2. So what I am getting here is, it is IA0 I am transferring to the left hand side. That is what I am getting is minus IA0 is equal to IA1 plus IA2. Okay. Now I am using the fault current equation. That is a fault current I know, it is IB plus IC. Just you have to substitute value of IB and IC from these two equations, IB and IC. Then what I am getting here is it is IA0 plus IA0 is 2 times IA0. Then here it is A square IA1, it is A times IA1. Therefore A square plus A into IA1. Then here it is A times IA2, here it is A square times IA2. Therefore once again I am getting A plus A square into IA2. Therefore it is a 2 IA0, but A square plus A is nothing but your minus 1. Just you have to work out for 1 angle of 240 plus 1 angle of 120, then it yields minus 1. Therefore A square plus A is nothing but minus 1 into IA1 as it is. A plus A square is once again it is minus, and IA2 I am retaining as it is. Therefore what I am getting here is the fault current is 2 times IA0 minus, both are here minus I am taking outside. Then what is the left out is IA1 plus IA2, IA1 plus IA2. However, IA1 plus IA2 is nothing but IA0. Just I am replacing this IA1 plus IA2 by minus IA0, so that the fault current what I am getting is minus IA0 of minus, that is plus IA0 plus 2 IA0, that is 3 times IA0. I told you that the fault current, that is IB plus IC, is nothing but 3 times IA0 because the fault is involved with a ground. Okay, this is how we have to justify our answer, that is the fault current in the case of double line to ground fault is 3 times IA0. Now our main focus is on to find only the fault current, that is IB plus IC, or it is 3 times IA0. Therefore we have to proceed with the sequence voltages. Sequence voltage, that is VA0, VA1 and VA2. Okay, that is VA0, I know VA0, VA1 is equal to VA2, that the relations were established from the sequence voltages, that is putting VB is equal to VC is equal to 0, and we are arrived at VA0, VA1, VA2 is equal to 1 by 3 times VA. Now using this relation, using this identity, just what I am doing here is I am comparing the VA0 with the VA1 and VA2 with the VA1. Just you have to look into here. That is I am using VA0 is equal to VA1. That is first two relations, VA0 and VA1 I am equating. Just I am substituting for VA0, that is minus IA0 Z0, and VA1 as it is, that is EA minus IA1 Z0. Just you have to look into here. That is VA0 I am substituting minus IA0 Z0 is equal to EA minus IA1 Z0 as it is. Now from this relation I am finding out IA0. From this I am expressing IA0 in terms of IA1. That is what I am getting is, it is minus sign is here, therefore it is taken minus sign here, that it is become minus A, it is become plus IA1. Therefore it is minus A plus IA1 Z1. Then this Z0 will come in the denominator, that is minus A plus IA1 Z1 divided by Z1 is the IA0 in terms of IA0 in terms of IA. Similarly, now I am using the relation between VA2 and VA1. That is I am equating VA2 and VA1. My main object here is to express IA0 and IA1 in terms of IA1, so that I am expressing the total current, that is IA current, in terms of IA1 only. We will come to know now. Now I am using VA2 is equal to VA1, that is VA2 is equal to VA1, VA2 is equal to VA1. Just once again you substitute the value of VA2, that is minus IA2 Z2, EA minus IA1 Z2. Here I am finding out the IA2 in terms of IA1. Therefore, IA2 is equal to, once again this minus sign is taken care in the right hand side. Therefore, this minus EA plus A1 Z1 divided Z2. That is IA2. Once again you can see here, this IA1, this is IA1, this is IA0 is expressed in terms of IA1. Here also IA2 is also expressed in terms of IA1. Now I know the boundary condition, that is IA is equal to 0. IA is equal to 0 in the case of double line to ground fault, because the fault is occurring between B and C to ground. Therefore IA is equal to 0. Therefore I am using that relation here, that is IA is equal to IA0 plus IA1 plus IA2 is equal to 0. Now I am substituting IA0 from this equation, that is equation number 1, and IA1 I am keeping as it is, and IA2 as replaced by this equation, that is in terms of IA1. Just you can look into here, substituting values of IA2 and IA0 from equation 1 and 2. Then what I am getting here is, it is IA0 minus EA plus IA1 Z1 Z0. This IA1 is as it is, and IA2 is replaced by minus EA plus IA1 Z1 Z2. You are observing here, this is only one unknown variable, that is I1, because EA, Z1, Z2, Z0 they are given value, Therefore, you take the I1 common and express I1 in terms of EA and Z1, Z2 and Z. Okay. Therefore, your IA1 is EA Z0 Z2 divided by Z0 Z1 plus Z1 Z2 Z2 Z0. That is one point here you have to remember. This Z0 is comprises of, it is a ZGO of generator plus 3 times Zn. That is external impedance which is grounded, that is Zn. That is the definition of Z0 that you have to take care of. It is not simply Z0 of a generator. It is comprises of zero sequence impedance of the generator. It is 3 times Zn of the neutral. That is grounded. That is 3 times the Zn. That you have to look into. Then I have got the value of I1. Then I am interested in the fault current. That is, if you know the I1 value, if you know the value of I1, then you can calculate what is the IA2. IA2 is just EA, Z1, Z2 are known value. IA1 you have to substitute from here. That is, you have to substitute IA1 here. Then you are getting IA2. Similarly, I am calculating for IA0 because IA1 already calculated here. That you have to substitute here, so that I am getting IA0. Then once I get the IA0, my total fault current is 3 times IA0. Therefore, you have to find out 3 times IA0. Once you know the value of IA1, IA2 and IA0, then it is possible for us to find out sequence voltages, that is VA0, VA1 and VA2. That is VA0 is minus IA0 Z0 and VA2 is minus IA2 Z2 and VA1 is EA minus IA1 Z. Once we know the sequence voltages, then you can find out what is the voltage between neutral and the line. That is VAN, VBN and VCN. I have got a relation, that is IA1 as the EA Z0 plus Z2 divided by Z0, Z1, Z1, Z2, Z2, Z0 and IA2 and IA0, and the total fault current is IB plus IC, that is nothing but 3 times IA0, and the one more voltage relation what I am getting is VA0 is equal to VA1 and is equal to VA2. If all the sequence voltages are equals, means that is a positive sequence, negative sequence and the zero sequence networks, they are connected in parallel. They are connected in parallel. That is demonstrated here. This is a positive sequence network, then negative sequence network and the zero sequence network, that is a terminal voltage of VA1, VA2 and VA0. This is their positive sequence VA1, negative sequence VA2, zero sequence VA0. All these are equal, therefore that is when the voltage across each network is equal, then they are connected in a parallel. Therefore these are all connected in parallel. This is how we have to analyze the double line to ground fault. Once we know the value of VA1, VA2 and VA0, then I told you that is we have to find out VAN, VBN and VCN. VAN is VA0 plus VA0 plus VA1 plus VA2, whereas your VB is and VC, in this case you have to get 0, that is can check by VA0 plus A square AVB A square VB plus AVC. Now that is you have to find out the value of that is you have to find. Once if you know the value of VA0, VA1 and VA2, you can find out VAN as VA0 plus VA1 plus VA2, whereas VBN is VA0 plus A square VA1 plus A VA2, and VCN you have to get as VA0 plus A VA1 plus A square VA2. However, if you are demonstrating this for this line to line ground fault, that is VBN you are getting 0 and VCN you are getting 0. This is how we have to find out VAN, VBN, VCN. Once we know, then you can calculate your line voltages, that is VAB is equal to VAN minus VBN. Of course it is a phase difference, and VBC can be calculated as VBN minus VCN, but in this case both B and VN, VCN are 0, therefore this we are getting 0, where VCA is, that is VCN minus VAN. This is how we have to find out. These are the terminal voltages. These are the terminal voltage under fault condition. These are line to neutral voltage. Line to neutral voltages. This is how we have to find out.